Hi, this is Dave Johnson with another edition of Math Off Topics. Before I start with my derivation of the convolution sum, and I'll say a little bit more about why I'm putting the word derivation in air quotes, I want to mention a couple of things. One, so I worked as an engineer for a number of years before I became a math teacher. I got my undergraduate degree in engineering physics. I worked as an electrical engineer for a while. And so I'm very familiar with engineering concepts, and I've seen convolution used. When I got my PhD, I did speech processing and I also did image processing, where we, for example, would convolve images with filters. And so convolution is a very important aspect of engineering. And I will say that, so as a math teacher, and I've taught everything from college algebra all the way through calculus 3, differential equations, linear algebra, and those kinds of courses. And at that level, you do not see convolution, except possibly in a differential equations course. But at the undergraduate level in a first semester differential equations course, you're probably not going to see much convolution. You might see it, maybe in an honors course or something like that. You might see the Dirac delta function when you're talking about the Laplace transform. But in terms of convolution, you probably don't get that until you get your engineering courses. So there's going to be a lot of people watching this video who maybe have a pretty strong undergraduate math background that don't know much about convolution. And hopefully this uh, video will help address some of that. The other thing I want to say is that I think professional mathematicians, and I respect them greatly, my master's degree is in applied mathematics. Professional mathematicians have a tendency to define terms and define formulas and things of that sort, sometimes without properly motivating those definitions. And one of the themes of a lot of my videos has been to find the motivation for those definitions. And that's what I hope to do in this video with the convolution sum. And then later, maybe another video, I'll do the convolution integral. So let's get into it. We're going to start with the idea that, well, first of all, let me show you what I mean by the convolution sum formula. So in general, if you have, um, say, functions f and g, and these are discrete functions. Discrete means that they're sampled uh, as functions of n, and n can be any integer. In this derivation, I'm going to allow n to go from negative infinity to positive infinity. If you're talking about causal signals, then oftentimes the function will be 0 for n less than 0. But uh, then you have the summation as k goes from negative infinity to positive infinity of f of k times g of n minus k. Now you might say, well, why is there a k here and not an n, for example? Or why does the n appear here in front and the k appears later? See, that's the kind of thing I want to address in this kind of so-called derivation. And to do that, we're going to start with the idea that this kind of sum, this convolution process, is based on a linear system, and in particular, um, linear time invariant, so LTI, linear time invariant system. Now, what do I mean by linear time invariant? Well, we're going to break that down a little bit, but I'm going to assume that this system, whatever it is going to be represented by an operator t that is linear and time invariant. And so you put in a signal, discrete signal, x of n, and out pops y of n. And so I'm going to notate that mathematically and say that the output y of n is equal to our operator or our transformation, whatever you want to call it, t operating on x of n. Linearity consists of two properties. one which some people call homogeneity. So we can say that T of alpha times x of n is equal to alpha times T of x of n. So constant multipliers can be brought out of the operator. And then the additive property, so T of, let's say, x1 of n plus x2 of n is equal to T of x1 of n plus T of x2 of n. And this can be generalized. I think most students at this stage will understand what we mean by linearity, but I just wanted to be clear that this also applies to operators of this type and also discrete time signals. So um, now this, I was going to say, this can be generalized to the sum of any number of signals, x1, x2, and so on, uh, by a property, a process of induction. So I'm not going to write that explicitly now, but we know we can do that. Okay, so now I'm also going to talk about what we mean by time invariant. So time invariant would say that t operating on, let's say, x of n minus k is equal to y of n minus k, where here we're referring back up to this expression here. So if you shift the time base by k units on the input, then you're shifting the time base on the output by the same amount. And that makes sense because the properties of the system don't depend on time. That's the idea. The physical world, the laws of physics are the same this moment as they were 10 seconds ago and an hour ago and so on. So time invariance is a very important property. So linear behavior and time invariance are two very important properties of many systems. Okay, now the final thing that we're going to need to do this is something called the impulse function and something called the impulse response. So let's define the impulse function, and I'm going to use the delta symbol, so delta of n. And you probably haven't seen this written down yet if you're not familiar with this topic, but I'm just going to give you a very quick hand graph here. So if this is 0, let's say this is -1, -2, +1, +2, then your delta function, your impulse function, let me write the word impulse here, impulse function. Basically, it's a unit impulse. This is 1, okay, height 1. And it's centered at the origin, at uh, time equals 0. And likewise, if I were to write something like this, so say n minus 2, delta of n minus 2, then I would get another graph. And let me label this. So -1, -2, +1, +2. So this is, all we're doing here is what you might in pre-calculus and other courses call a function transformation. So it's a horizontal shift to the right 2 units. That's what we mean by by this delta of n minus 2 or n minus k, where k is some value, and the k could be positive, k could be negative. Okay, so if it's positive, we're shifting to the right. If it's negative, we're shifting to the left. Okay, So once you have the delta function, and we need to be careful that we distinguish between the delta function that's continuous variables and the discrete delta function for discrete time systems, because their properties and behaviors are very similar, but they're somewhat different. And so these are discrete time delta or impulse functions. So, and then let's go back to our linear time invariant system. If I put in a delta of n, then what do we get out? Well, we should get the t operating on the delta of n, and we're going to define that to be h of n. And this is known as the impulse response. In other words, so you can think of the delta function as a little bang on your system. Not too much of a bang because that might turn the system into something that's nonlinear. You know, if you take a hammer and flatten it, you know, that's obviously going to be nonlinear. You're going to get a nonlinear response. But if you're talking about something like you know, a snare drum or something, and you just tap on it, so that could be regarded as an impulse. So tap, and what is the response of the system? Well, what you're going to get is an impulse response. And if we know the claim here is if you know the impulse response to a linear time invariant system, you can predict the response to any input um, that isn't going to change the properties of the system. So, okay, so let me be explicit about this. So h of n is equal to t operating on delta of n. And now we're going to start to use some of the linearity properties. So first let's shift it. So h of n minus k is equal to t of delta of n minus k. So this is the time invariance property. And now we're going to multiply um, your delta inside by, let's say, x of k. And if I do that, let me just go ahead and write this here. So t operating on x of k times delta of n minus k. What's the response going to be? Well, multiplying by that inside your operator, because of the homogeneity property, we can write this as x of k times h of n minus k. And those of you who know how this works may see where this is going. Okay, so my next step is to sum all of these responses from negative infinity to positive infinity. Now, some of you may say, well, what about one-sided convolutions? I think if we understand the case for k goes from negative infinity to positive infinity, we can easily derive what's going to happen if k goes from 0 to infinity. So I'm going to do the negative infinity to positive infinity. So if we sum, let's say k goes from negative infinity to positive infinity of x of k times h of n minus k, I can say that that's equal to, and pull the summation inside by the additive property. So k equals negative infinity to positive infinity x of k times delta of n minus k. So another way to look at it is if I sum, so here I have just this term by itself, but if I sum a bunch of these, well, that's the same as the sum of the outputs. That's the additive property. Okay. Now, here's the kicker. So because of the way the delta function works, the impulse function, if I look at this sum, I can write this as x of n. Okay. And the reason we can do that is because each xn, let's say n here, if we shift the delta by k amount and multiply by that x value, we're actually picking up the x sub n quantity for that value of n. And so this is what's known as the sampling property of the delta function. And I may put out another video that explains this in greater detail. But if we accept this fact, and this may be the magic step in this derivation, but if you believe this, then what we get is on the right-hand side, we have this is equal to t operating on x of n. And if you remember where we started from, come back up here. So y of n is equal to t of x sub n. And so I could write this as y of n. And therefore, y of n is equal to our sum here. K goes from negative infinity to positive infinity, x of k, h of n minus k. And that is the convolution sum. Now, mathematicians like to come up with notations that make it a little easier to write, make it easier to manipulate. I'm completely in agreement with all of that. And so you might write that as x, and then this convolution symbol, asterisk, h. And if we put that in parentheses and label this with the n in brackets, that means that that is a function of n. And so we're saying that y of n is equal to this convolution. And so that's where this comes from. And so understanding every step in the process using a time invariant linear system, you get convolution. So I hope this has been helpful. If so, please like and subscribe, and I'll see you in the next video.